picture this. You are standing right at the edge of a massive wilderness.
Just a huge, sprawling landscape.
Exactly.
Yeah.
And you are trying to decide the absolute safest path up a towering mountain.
Right.
Or maybe you're looking for the easiest, least exhausting route along a winding river. And to make this crucial decision, you are armed with nothing but a flat piece of paper covered in squiggly brown lines.
Just squiggles. Yeah, it sounds like a classic survival scenario.
It really does. It's the kind of analog navigation challenge that map enthusiasts and seasoned hikers know intimately. Welcome to this custom deep dive.
Today, our mission is exploring a really fascinating 15-minute Earth science activity.
Yeah, from the S3 GeoInquiries collection.
Right. Specifically focusing on topographic landscapes and scale navigation.
It's a great piece of source material.
Okay, let's unpack this. Because these simple maps unlock the 3D secrets of our national heritage sites. And the specific site we're looking at today is Yosemite National Park, which is undeniably iconic. But before we even get into the maps, we have to set the broader context here.
Right, the bigger picture.
Exactly. We have to ask why dedicating these massive areas like Yosemite as national parks matters in the first place.
It's a huge commitment of land.
It is. And as urbanization increases, as we just keep pouring concrete and expanding our cities, we desperately need these natural areas.
For ecology, right?
Oh, for sure. We need them to preserve ecology. But the source material also notes we need them for rest, for relaxation, to reconnect to global systems.
Like a physical reminder to live sustainably.
Precisely. Standing in Yosemite, it just recenters your understanding of your place in a much older ecosystem.
So, bringing that enthusiastic energy back to the map itself, let's break down the visual language of these maps.
The secret code, so to speak.
Exactly. You look at the map and you see these smooth, brownish parallel lines. Those represent elevation.
Yeah.
And then you have these blue squiggly lines.
Which represents surface waters, creeks and rivers.
Right. So you have the earth and the water clearly laid out.
What's fascinating here is the golden rule of those brown topographic lines.
Which is what, exactly?
They rarely touch or cross.
Never.
Well, almost never. And the logic is actually pretty simple. Since each line is a specific elevation above sea level, a single point cannot be two different elevations at once.
Because you can't be at two heights at the exact same time.
Exactly. The only rare exception would be something like a sheer cliff or an overhang.
Where the elevations literally stack vertically.
Right. But generally, the lines stay separate. And you can use this to spot landforms. Take a valley, for instance.
How do you spot a valley on these maps?
On the map, you can tell you're looking at a valley because the elevation numbers get smaller as you move toward the water source.
So, like moving toward the Merced River in Yosemite.
You got it. The numbers drop as you get closer to the water.
That makes total sense.
Yeah.
And this whole activity actually aligns with a specific educational standard, right?
Yes, the Next Generation Science Standard, or NGSS.
NGSS MSESS 24, to be exact.
Right, which is all about developing a model to describe unobservable mechanisms.
I love that phrasing, unobservable mechanisms. Because when you look at a flat piece of paper, the height of a mountain is totally unobservable.
The z-axis is just missing.
Exactly. The map is the model that lets your brain see that missing dimension. Let's actually take a virtual tour of Yosemite using these map patterns.
Let's do it.
So if you're looking for hills and mountains, take the famous Half Dome, for example.
A massive piece of granite.
Oh, absolutely towering. On the map, it appears as concentric circles or closed figures.
Like a bullseye.
Right. But then, in contrast, you have very steep areas like the El Capitan Cliff.
Which looks totally different on the map.
Completely. The parallel lines are packed so close together.
Almost merging into a solid band of brown ink.
Because the elevation is changing so drastically over such a short distance.
Right.
And then you look at flat areas, like the campground.
Which is where you want to sleep, ideally.
Definitely. And the campground is noticeably missing those tightly packed lines.
Just wide open space between the contours.
Right. Here's where it gets really interesting. Because not all lines look exactly the same. We have to introduce the concept of index contours.
This is a crucial detail for reading these maps.
Yeah, some lines are noticeably thicker. And they feature the actual elevation number printed periodically along their length.
So let's walk through the map math here. You can use these index contours to find the contour interval.
Which is the vertical distance between each individual line.
Exactly. So the rule of thumb is that every fifth line is an index contour.
Okay.
So if you take the difference in elevation between two index contours, let's say the difference is 200 feet.
All right, 200 feet.
and you divide that by the 5 intervals between them.
200 divided by 5.
You get a contour interval of 40 feet.
Wow. So every single thin line you cross represents 40 feet of vertical climbing.
Or 40 feet of descending.
Yeah.
Exactly.
That turns a squiggly line into a very real measure of sweat and effort.
It really does. And if you follow that math, tracing those intervals all the way to the top, the top half dome sits at a towering 8,800 feet.
8,800 feet. That is just incredible to pull straight off a flat image.
If we connect this to the bigger picture, that's really the core learning outcome here.
Predicting the implications of these landforms.
Right. Specifically for health and safety and recreation. How does knowing this math actually keep you safe?
Well, let's talk about the reality of climbing Half Dome. It's a notoriously tough hike.
It's grueling.
And the map reveals exactly why. If you look at the southwest slope, the lines are spread further apart.
Meaning it's gentler, much easier to climb.
Right. But the northeast trail, the lines are so tightly packed, it's incredibly steep.
It's so steep that the actual physical trail requires 2 metal handrails built right into the rock just to assist hikers.
You literally have to pull yourself up. And you can see that hazard on the map before you ever set foot on the mountain.
Exactly.
Yeah.
And using the digital measurement tools in the activity, you can see it's about a 3-mile distance from the top of Half Dome down to where the trail meets the river.
So you're balancing 3 miles of distance against thousands of feet of elevation change.
That is a serious physical toll.
Let's compare some other hiking options on the valley floor.
Okay.
Say you're starting at the campground. You can hike a couple of miles up Tenaya Creek, which is north of Half Dome. Or you can hike up the Merced River, south of Half Dome. The map shows that hiking Tenaya Creek is much flatter.
The lines are spread wide apart.
Right, less strenuous. But hiking up the Merced River, the lines cross the water tightly. It's a steep, exhausting incline.
So it's not just about finding your way, it's about optimizing your physical energy.
Exactly. But it scales up from just being tired to avoiding actual life-threatening hazards. Let's analyze the water flow.
This is where reading the lines is literally life-saving.
Right. So when contour lines cross a river, they form a V shape.
And those V shapes always point upstream.
Pointing toward the higher elevation source.
Right.
So looking at the Merced River, those V shapes show that the river flows west to southwest.
Draining out toward the lower valley.
Crucially, the map shows that the Merced River to the east drains a much bigger valley.
A massive drainage basin.
Yes. So when a storm hits that huge eastern basin, all that water acts like a giant funnel.
It catches all that rainfall and channels it straight down into the narrow confines of the river.
Which means those upriver canyons are incredibly susceptible to flash floods.
Sudden and violent flash floods. And you can predict that just by looking at V-shapes and the width of a basin on a map.
That is a profound survival skill being taught to middle schoolers.
It really is.
Which brings us to the tech making this possible. We have to highlight the platform itself. It's ArcGIS Online.
Brought to us by Esri.
The company known as the Science of Where.
That's their catchphrase, yeah.
And this specific 15-minute activity is part of a larger collection. 15 free web mapping activities.
Created to support the White House Connected Initiative.
Which is awesome.
Ugh.
And they are completely device agnostic.
Meaning you can run them on a high-end laptop or just a basic tablet in an underfunded classroom.
Right. They use an inquiry-based model. It's not just rote memorization.
The students actually have to interrogate the data to solve problems, like finding that flash flood risk.
Exactly. And these activities cross-reference perfectly with standard middle school earth science textbooks.
From publishers like Glencoe, Holt, McDougall-Littell, and Prentice Hall.
It bridges the print and digital divide seamlessly.
This raises an important question. What about educational accessibility?
Right, because professional GIS software is usually pretty expensive.
Very expensive. But this mapping platform is freely available to public, private, and home schools.
Completely free.
Yes. And they do offer school subscriptions that provide additional security, privacy, and content features for districts that need advanced admin control.
That removes a massive financial barrier.
It does. But my favorite part is the licensing. It uses a Creative Commons license.
Specifically, CC BY NC SA.
Right, which basically means it allows the curriculum to be shared and adapted.
So a teacher in a totally different state could take this Yosemite hazard assessment and adapt it to their own local topography.
Exactly, making it hyper-relevant to their specific students.
So what does this all mean? When we look at everything we've unpacked today, the key takeaway is that topographic maps, are not just academic exercises.
They are far more than that.
They are vital tools that translate a flat piece of paper into a 3D landscape. They tell us where to walk, what hazards to avoid, and how to safely navigate our national heritage.
They teach situational awareness.
Absolutely. And if you were listening to this and want to test your own skills, you can try the National Park Bird's Eye Quiz. It's mentioned right in the source material as a great practical application.
It's a highly recommended exercise.
Before we go, we want to leave you with a final lingering thought to explore on your own.
Something to mull over.
Right. If learning to read a few squiggly brown lines on a map can reveal the safest path up an 8,800-foot granite dome.
And warn us of invisible flash flood zones.
Exactly. What other hidden patterns in our everyday environment could we navigate more safely if we only took the time to learn their visual language?
Whether it's in nature or even in our cities.
It's definitely something to think about. Thanks for joining us on this deep dive. We'll see you on the next one.